So we're going to proceed with our understanding, our work on classical groups. And as a reminder, this is our book. And I want to quickly talk about this for a moment. The idea is that, as I said in the first lecture, this is like my favorite book. It's certainly not the only book, but it's my favorite book. And it's sort of the book we're going to use as the go-to reference for this course. And what I've realized as I'm doing this course is how much I've relied on this book throughout my career working on this material, my time working on this material, my intellectual journey through the mathematics through mathematical physics and physics. And it's great, but now that I'm actually talking about these things, I have questions start to come up. And in particular, because these books are I'm not the only guy who likes this book, right? This is a definitive book in this subject, but it's also true that they're not totally complete, and they have to start somewhere. And of course, nobody ever starts their mathematical texts from elementary set theory and builds everything up from elementary set theory. In fact, those endeavors to build up all of mathematics from elementary ideas are generally subjects all in of themselves. They always start somewhere, is my point. And in the case of this, where they started in the section of classical groups, part of that introduction, part of that starting point was his definition, Gilmore's definition of the metric. Of course, any definition of the metric has to assert that it's from the Cartesian product of the vector space into the underlying field of the vector space. And I'll remind you also that when I identify a vector space, I give it a name, I assert that there is a basis, a dimensionality, which we'll call capital N in this case, and an underlying field that supports the vector space. And again, right away, this issue of, for my entire time, I had just assumed, because Gilmore said it, that the quaternions were a field. They're obviously not, under most definitions, a field. So this really represents for Gilmore what we would call in the modern parlance, or in the common parlance, normed division algebras. But basically being concerned with this being the real numbers, the complex numbers, and the quaternions, right? So then he immediately offers his version of what a metric is, which is very complete. And what's nice about his work is his definition of the metric is really about as general as we can have. The only real demand, of course, is that it is this map. It's a Cartesian product of the vector spaces into the fields, and it has this type of linearity where we're linear in the scalars that are in the second slot, and we're linear in the scalars that are in the first slot, but the scalars in the second slot come out on the left, and the scalars in the first slot come out on the right. And he does the left-right thing only to accommodate the quaternions. Obviously, if we're dealing with real numbers or complex numbers, then this is real or complex, and of course alpha and beta would be real or complex, and everything commutes, and it doesn't matter which way you pull things out. But the quaternions don't commute, so he establishes this unambiguous order. It didn't have to be this particular order. It could have been something else, but Gilmore believes that notationally it is the most advantageous to do this. But then Gilmore says that, wait, there's another possibility here. And he offers us this sesquilinear metric. He called this bilinear, and then he calls this sesquilinear. So actually, he does it one word, no hyphenation. So now it's like, okay, well, what the heck is that all about, and why? Well, doesn't do much damage to this, right? A complex conjugation still keeps this answer in F. But doesn't this seem a little arbitrary, right? Doesn't it seem arbitrary that this guy, for some reason, we're now going to suddenly throw down a complex conjugation? Now, complex conjugation, we know, is a pretty, standard operation on complex numbers. It's everybody learns about it for a long time. It's an option, But why, right? This seems a little bit out of the blue. There's metrics, bilinear and sesquilinear metrics. So I wanted to discuss that because in explaining all this stuff, the goal for classical groups is to understand how all these different groups affect all these different groups are basis changes of metrics of vector spaces that leave metrics unchanged. And the idea is we have to sort of understand all the different possible kinds of metrics. And right now, this is the metrics that Gilmore offers, but he doesn't sort of explain why this is all the possibilities. So I kind of wanted to look in at why this thing is even a thing, right? Why is this even a thing? But before I go that, I want to make it clear that Gilmore asserts that there are other restrictions we could have on a metric. We could have V1, V2 equals V2, V1, or equals minus V2, V1. That's a possibility, right? We could demand that kind of symmetry, right? We could, or if for real numbers, or we could demand it to be the complex conjugate like that, or the anti-complex conjugate. Those are demands we could make. We could also make the demand that V1, the inner product of every metric with itself, right, has to be greater than or greater than 0 and equals to 0 only when V is 0, right, for example. And he doesn't impose any of these, right? And that's good because this one in particular is not necessary, but the symmetry requirements aren't necessary. And the greater than 0 part isn't necessary. And in fact, as we've all seen in general relativity, or I shouldn't say as we've all seen, saying as you have all seen or as you all know, that's actually a microaggression. I know there was a little bit of a PC outrage on this point, or counter PC outrage about using that term on university campuses, as you know, right? And I was a little caught by surprise when people said, as you know is not something you should say anymore. We should get rid of this. And I immediately agreed. I was like, yeah, that is actually a no-kidding microaggression. When you have people who say as you know a lot, look at them, pay attention to those people, right? Because they are, the people who say as you know are really trying to say something else. And it's worth paying attention to. So, but I fall into that trap. As you know, if you've studied general relativity, well, not everybody has, right? And me saying as you know is just making a big ego scoop like, oh, I've understood and researched general relativity. And of course you have too, right? Like, as you know, when you orbit the Earth in the space shuttle, because I'm an astronaut. Oh, you're not an astronaut? Oh, sorry. Yeah, let me see if I can explain this to you. It's a microaggression, and I agree that it should be. We should look carefully at. We should root those things out. Anyway, sorry. So what about this, right? What about these? The purpose I'm trying to get at here is why sesquilinear forms. So let's talk about that. All right, so let's begin with a mathematical universe that contains one vector space. And we know from previous work that this mathematical universe really can't contain one vector space. It's got to have something else to it. We've already shown in the What is a Tensor series that once you have this vector space, you actually have a collection of at least two other sets we've talked about. One is the set of all linear transformations. Actually, you know what? I don't think we talked about the set of all linear transformations, but that's the set of all maps from V back into V, right? And as long as we have the set of all of them, where the mathematician who's talking about all of this stuff doesn't have to make any decisions and doesn't have to add anything, that mathematician can talk about the entire set of all possible linear transformations, but we can't single one out as being important. So those exist. In addition to this vector space, all of these maps of linear transformations must exist. Now, the one we did talk about at great length, was the mapping of all the maps from V into the underlying field, right? And we called that V star. We called that the dual space, right? And that is a vector space of maps that go from V to V star, or V to F, right? These are maps that go from V to V. And those are maps that go from V to F. So we talked about these a lot in what is a tensor, and they all exist. It's the set of all the maps. Again, we can't select any one. There's no way, none of the facts given in our universe, which is just the vector space, the basis, the dimensionality, and the underlying field. That's all you need for a vector space. Well, I guess, obviously it has a defined addition property, right? And there's a zero element, obviously, right? So all the properties of a vector space are there. Let me make those black because it's part of the vector space. The dual space is its own thing, and you could actually say, well, that pops into existence, right? And it has its basis E mu, it's n-dimensional, and it has the same underlying field. So we talked a lot about this one in the previous lectures. We didn't talk so much about this, but if you've studied linear algebra is all about that, eigenvectors and linear transformations and the kernels of those transformations and all that stuff. The one that we didn't talk about yet at all that does exist is F back to F, right? That's just like V into V and V into F, you can have F into F. And since we're only interested in this case, we are only interested in certain maps. Because remember, the V into V maps have to preserve the structure, right? You can't have a map that returns a vector, but the vector doesn't obey addition, right? The maps from F to F that matter, remember, F is a field, so it has an addition and a multiplication. It has a zero and a unit, where the unit is the unit of multiplication. I guess I should switch those around. The zero is the identity for the addition, and it'll have an identity for multiplication, right? And so the field has to preserve all of these properties under any mapping, meaning any mapping has to preserve all of this addition and multiplication property. In other words, I'm struggling to say the mapping that we care about are isomorphisms, and they're field isomorphisms. And because it's the field into the field, it's really a field automorphism. Okay? So we're interested in the field automorphisms associated with R, C, and Q. Now, I'm not an expert on this subject, but I can tell you that an interesting fact and an important fact that we need to know here is that there is one field automorphism for the real numbers only, meaning the set of all field automorphisms for the real numbers. How about if I do, how would I write that? I guess I would write that automorphism F, like that. The set of all, no, I think the way you would write it is the automorphisms of R, it's just the identity, right? The identity automorphism is all you have. And the reason is, and we won't go through any proofs here because these proofs are actually pretty fundamental and hard. But, they're not as hard as some of the other proofs we've done. I just don't want to get bogged down in it. But any automorphism of F into F, where, remember, automorphism means F of A plus B must be F of A plus F of B, and F of A times B must equal F of A times F of B, right? That's how this has to work, right? In order for that to work, F of 0 has to equal 0, and F of 1 has to equal 1. And in fact, I think F of any rational number ends up having to equal the same number, right? And So field automorphism is very demanding. And for the real numbers, there's only one. And these restrictions mean the identity is it. In other words, I guess you could say there's no non-trivial field automorphism for the real numbers. For the complex numbers, there are two. There's the identity automorphism, and then I'll call DI, the identity morphism of a complex number of alpha equals alpha, and DI is the complex conjugation. Those are the only two. Now, I got to be a little bit careful here because this is getting in mathematical territory. As simple as this sounds, this mathematical territory is actually a bit bizarre. There are only two continuous field automorphisms, which means f of alpha, that function, which would be f of, say, a plus ib, which can be interpreted as some other function of two variables, a, b. As a function of two variables, these are the only two automorphisms that are continuous. Apparently, there's actually an infinite number of field automorphisms of the complex numbers, but these are the only two that are continuous. All of the others are called wild, and their existence is known only through the axiom of choice, right? The axiom of choice, or Zorn's lemma. I haven't worked through the proof, so I don't know which one of these is actually using. It doesn't matter. I mean, ultimately, the point is that the wild field automorphisms of the complex numbers are known to exist because of a proof that depends on the axiom of choice. That's another way of saying that is they exist, but we can't construct any. Because if we could construct one, that would be the equivalent of proving the axiom of choice, which is presumably not possible to do within the confines of mathematical logic that we use. We have to add the axiom of choice to our fundamental system. We can't prove it from within the system in principle unless things change. The point is these are the only two options. And a similar thing applies for the quaternions. I won't get into that. It's not because I don't have enough time. It's because I can say things with less confidence about the quaternions because I don't know as much about them. In this whole idea of all the possible automorphisms of quaternions. But I'm presuming that it has the same problem. It's got a lot of wild ones, and it's got the conjugation. Quaternionic conjugation is the only alternative automorphism for available. So the point is we now have, these are the things that we have. We have these linear transformations, maps from V to F and F. And we can work with those objects all we want. And our goal is going to be to produce a map from V cross V to F. So we want a map from V cross V to F, and that map is going to be the metric. And when we have the metric, we're going to add it to the metric space. We want to talk about all possible ways we could do this. What are all the possible ways we could do this? And those ways involve defining these three things using these three tools. These tools are at our disposal. If we want to find one map, I can pick something from here, I can pick some stuff from here, and I can pick some stuff from here and put it together in some way to get this map. And when I think about all the possible ways to do that, I better come up with, this is it. This is it. And that's why sesquilinear forms are important, because it's part of this process of coming up with all the possible ways of making an inner product using just the tools available to us. All right, so let's have a little bit of a look at that. So we'll start with the maps from V to F. The maps from V to F we know we define with these metrics where we list these numbers, EI, EJ. Once we give you this, then you can map any vector to F. In other words, once you know how these inner products work for a basis set, you know how they work for everything. So ultimately, you have to supply to get an element of the set of all maps from V to F. You have to supply these numbers, and there will be exactly n squared of these numbers that you need to supply. And these numbers are numbers from the field, right? So let's think about everything in terms of complex numbers right now, because so complex. So these guys have to be some complex number, all right? So that's actually the easiest one, right? Well, that is an easy one. I guess the easiest one is I can choose. So once I start with that, now I say okay, my goal is to make a function from V cross V to F. An element of V cross V is an ordered pair V1, V2. So it's fun because you can look at these ordered pairs and you can say, oh, well, that's clearly an element of this. But if you think of this as this ordered pair as an element of this set, then this doesn't make any sense, because an element of this set cannot equal gamma, where gamma is an element of the field. So it's convenient that this looks like an element of this set, but we're going to think of this as a machine with two slots that takes two vectors and produces a real number. And I can express that real number as gamma or as this. So once I've done this, then I automatically, because the nature of my vector space, I get to write V1 mu E mu, V2 nu E nu, right, equals gamma. And now I have this inner product with a vector. What I'll do is just to mark the little vector, there's the basis vectors, and scalars, right? V1 mu, V2 nu are scalars. And this is one of those interesting notational things where I've named the two vectors V1 and V2. So I've given the subscript, the name of the vector includes a subscript. The superscript is there for the indexing convention, right? So this looks like a subscript-superscript relationship, but this subscript is not a summation index or a countable index. It's just an index to name the vector. I probably could have done, since I'm using two, just V and W and Z, right? In which case we would have ended up with V mu, E mu, W nu, E nu, right? That's probably the better way to write it down, so I don't have these subscripts that aren't really indices. So once we've got this, and we know that our goal is to create an inner product, and we know that the rules of an inner product are going to be linear, right? We want linearity in these things. Now, we still kind of have to talk about this complex conjugation, but we definitely want linearity. So we know that we're going to want this to somehow come out. Now, whether it comes out on the left or the right side, that's immaterial, because, as I said, for the complex and real numbers, it doesn't matter. And for the quaternions, you're just choosing a way of writing it. And if you want a different outcome, you would put it in a different fashion. You would if these were quaternions, you could arrange the final ordering by whether or not you put it into the left slot or the right slot. But we're going to now use the convention that we've decided, and we're going to say we're going to say W nu, E mu, E nu, V mu equals gamma. Now we've done that, but we're a little abrupt because we haven't used these maps, we have used these maps, but we've made the choice. We've basically, by just writing that down, we have forced ourselves into the choice of using the identity automorphism when available, or that was the only automorphism we've used here, right? In other words, this is just defined arbitrarily, right? So we don't change that. But when we pull these out, we can also say, well, once you pull them out, the next step, right? The next step is to apply the automorphism. So I guess what I should do is I say you pull them out, and then you apply an automorphism on F. You have the right to do that because it's a thing you own. It's a thing that exists in your vector space creation. You have F and all the sets from all the automorphisms from F to F. You can use that. So, well, what would you do? Well, you could choose the identity automorphism like this. That's one choice, all right? So you only have two choices. You have the identity automorphism and complex conjugation. So if you use the identity automorphism on both slots, you get the bilinear metric. If you use the identity morphism on one of the two slots, you get the sesquilinear metric. And if you use the identity on both slots, I don't know. That's certainly not covered in Gilmore's definition of how this works, right? But what I believe is going on there is that ultimately any metric that's conjugate linear in both slots is ultimately the equivalent of some bilinear metric, meaning you redefine these guys in the appropriate way, and this is no different than this ultimately, right? So I'm pretty sure that's what's going on there. In fact, what I think is happening here is once you're done with this product, you can also then, so we've had to introduce this field automorphism at this point, at this stage, right? We have to decide, are we just going to throw down the field automorphism on the left and the right side? And then when you're all done, you can throw in the field automorphism again, because this is still an element of the field, this whole thing. So we could map it again, right, through a field automorphism. And I think the combination of all of those things shows that these metrics are ultimately equivalent in behavior to those metrics. So, which leaves us with just two real distinctions. And the left-right stuff is completely notational convention that can all be made equivalent. So this is why. So the ultimate reason why we have bilinear and sesquilinear as our important two choices comes to the fact that fields have only these two credible automorphisms available, and you have to really account for them. You have to say, look, if you're interested in all the mappings from here to here, well, all the ways of doing it are all the ways you can define this guy, and all the ways you can handle the field elements using automorphisms. That, where the need for automorphisms is designed because you need to preserve the field structure. And that is why you have bilinear and sesquilinear matrix forms available to us. So I wanted to cover that just to show that, if you read Gilmore, this stuff here kind of feels a little arbitrary. He'll just say there's bilinear and sesquilinear metrics, and then all of a sudden there's complex conjugations involved. And that actually percolates through all of physics education, where you talk about Hermitian operators, which are the conjugate transpose of things. And the underlying reason mathematically has to do with the possible ways, Hermitian operators, for quantum mechanics, it comes down to this. You can take the reason that you have complex transpose operators for quantum mechanics is because of this, is because of you're dealing with inner products on complex vector spaces, Hilbert spaces, and these rules apply. Bilinear and sesquilinear metrics are your two big options. And that's where Hermitian conjugation comes in. Now, Hermitian conjugate, those things actually do have rules like this, right? Where if you switch the order, you add in you demand a symmetry that includes just not only symmetry, you switch the order of the guys in the inner product, but you also throw down again your optional choice to use one of these two automorphisms, right? That is a totally legitimate use. Now, in this case, one of the goals is you want to make sure we like it that when that the inner product of V with itself, we like that to be a real number, right? We like that to be a real number. So this demands that this guy here ends up being a real number, because the only way something can equal its own complex conjugate is if it's real, right? So having this kind of symmetry is designed to give us this kind of outcome. And you could also have this kind of symmetry too, by the way. And all of these things have a place. These are all, but the point is, the reason that they're there, the reason this is interesting, and the reason we're absorbing every possible option available to us, and we have left nothing out. So if you say, well, Hermitian conjugation and sesquilinear forms, it seems like these random things. No, it's a complete exhaustion of what's available to us once we stipulate the existence of a vector space. Now, I didn't talk about linear transformations, right? We could have added those in, right? This guy here, what I did is I immediately went to the inner product equals gamma, and then I kind of flushed through, and I worried about this, and we worried about this, but we didn't worry about this, right? So I could have made a linear operator there and added a linear operator there, right? Turns out that doesn't matter too much, because A and B, they're both elements of the vector space. So any choice I make can be just sort of absorbed by just changing the basis, right? You just change the basis, and those things start becoming less important. I mean, the fact is given that these are vectors, throwing in an A and B, you can accommodate that simply by redefining this, is I guess the way to say it, not changing the basis per se. But by changing this guy, you can essentially account for A and B. So these guys don't really matter much at all. But these guys do. These guys are important. And fortunately, there's such a small number of them that we can accommodate every possibility. And again, that's where sesquilinear stuff sort of comes from. Okay, so next time we'll move on from here and start talking about all of the possible different kinds of metrics that matter to us. Oh, wow. Wait, before we go, this logic applies to the vector space itself. We have in the vector space a defined addition and a scalar multiplication, right? And the idea of this scalar multiplication is that some element of the field multiplied by some vector should give us something we call alpha v, right? Now that's the way the vector space is defined, but that's not exploiting both possibilities, right? We haven't exhausted both possibilities. Our vector space definition only uses the fact that if we write, say the vector multiplication or the scalar multiplication is a little circle there, we could say alpha circle some vector v, right? That could equal alpha v, or it could equal alpha conjugate v, right? It could equal the automorphism. If you make this choice, very typically that vector space, it becomes suddenly a different vector space. Maybe I'd make it green instead of black. That's not the same vector space. If you define the multiplication with this conjugation in it, you've really created a different object, right? And the elements of that vector space are identical, right? The elements of a vector space with this choice are the same as the elements of the vector space with that choice, but the multiplication property is just different. And frequently, when that does show up, that the vector space with the alternative multiplication is differentiated with a bar over it. So when you create this vector space here, and I said it automatically creates the dual space, and it automatically creates all the linear operators, and you get those automorphisms on F. You also get V bar too, in principle, because there's no reason why, or you get a V bar for each automorphism on F. if you're dealing with, there are fields out there that have more than two automorphisms, right? We're only interested in the reals, complex numbers, and quaternions here. But if you are choosing some field that has more automorphisms, then you have to account for all of those. Okay, so I just wanted to point out that this logic of full exhaustion applies to the vector space itself as well. And that full exhaustion leads to this guy, where the multiplication property of taking a scalar and multiplying it by a vector in the space actually ends up with this guy. You're actually, the literal multiplication is with the conjugation. I guess to make sure that's totally clear on how that would work, if I had a vector v, and that was v1, e1, plus v2, e2, plus v3, e3, and I wanted to do alpha v, normally what I would have is alpha times v1, e1, plus alpha times v2, e2, plus alpha times v3, e3, right? That would be the answer. This would be the resulting vector, which we would usually just write as alpha v. Well, in this vector space, this statement would end up looking like this, right? And that's a different vector. It's a different vector. It's not the same one. Okay. All right, so I'll see you next time.